Now that we've looked at the history of the atom and how we've got to our model, we now need to pay attention to the atomic structure. So the first thing we need to look at are what are the three subatomic particles that were discovered. They were the proton, the neutron, and the electron. We need to know the location of these particles. So our positively charged protons are in the nucleus of the atom, as well as our neutral neutrons. Then our negative electrons are found in the energy levels or the electron cloud. So as we look up here, the blue E's with the negative sign, this represents the electron with a negative charge. And for the electron, the mass, we're going to count it as 0 atomic mass units. The reason we aren't even going to consider the electrons when we look at the mass is because they are so much lighter than our protons and neutrons. Our protons are positively charged, and they have a mass of 1 atomic mass unit, or 1 AMU. The neutron has a neutral charge, or no charge at all. And it has an atomic mass of 1 atomic mass unit. Now, with the electrons, as I said before, we're going to count those as 0 because to equal the mass of 1 AMU, you need almost 2,000 electrons. So it's almost 2,000 electrons to equal 1. So its atomic mass unit just doesn't account for a lot. So we are not going to count it when we talk about atomic mass. This table in your packet is so you can organize that. We said our charge was positive for the proton, neutral for the neutron, negative for the electron. The symbol is a lowercase first letter of the name and then its charge as a superscript. The location, we saw where we drew them in our picture, that this was in the nucleus. The neutrons were in the nucleus. And our electrons were in the energy levels or electron cloud. The mass, we said, of a proton was 1 AMU. A neutron was 1 AMU. And the electron, we're going to count it as 0. The The charge on the nucleus of the atom is positive because in the nucleus there are positive protons and neutral neutrons. So the neutral does nothing to the charge of it. So the only charge that there is in the nucleus is the positive protons. So that's why it has a positive charge on the nucleus. Now, since in an atom, the number of protons equals the number of electrons, then we know that means the overall atom in itself is neutral in charge, because our positive protons equal the number of our negative electrons, so they cancel each other out. An atom's mass number is determined by how many protons and neutrons there are in the nucleus of the atom. You take the number of protons and you add it to the number of neutrons, and that gives you the mass number for that particular atom. Protons determine the identity, so that's a particle that never changes. However many protons it has, then doesn't matter what chemical reactions take place, it will still only have that number of protons. If the number of protons changes, then so does the element you're working with. So we know that the number of protons then is unchanged. The subatomic particles that can change are the electrons and the neutrons. We saw the electrons move when we did the charge lab, and we're able to create charged particles and charged objects. The neutrons we'll talk about in a few moments about what happens when they change. Changing of the electron. So in the charge lab, we looked at the fact that whenever we moved the electrons through rubbing the balloon on your head or rubbing the paper towel on the pen, then we moved those electrons and it charged the particle. We call those particles, when we talk about atoms, we want to represent them as something different because they're no longer neutral. So we call those ions. And if we refer to them as ions, that means they have added or lost electrons. So if we look at a sodium atom has 11 protons and 12 neutrons in the nucleus. Then it has a total of 11 electrons. If it loses one electron, then that means instead of having 11 protons, 11 electrons, and 12 neutrons, so we can see 11 positive and 11 negatives. 11 minus 11 gives us an overall charge of 0. So this is the atom. But if it loses it in a chemical reaction, it gives it away to something else, then now if we look at it, there are only 10 electrons, and we still have 11 protons, and we still have our 12 neutrons. But now, when we take our 11 positive protons and subtract the 10 negative electrons, we end up with a 1 that's positive. So this sodium atom, when it loses its electrons, will become positively charged. So the sodium ion has a charge. It's no longer neutral like our atom was. It now has a positive 1 charge. Now we're going to look at a sulfur atom that is going to gain 2 electrons. So sulfur has 16 protons in the nucleus and 16 neutrons in the nucleus. Then it has 16 electrons. So for the atom, we see that the number of protons, 16, the number of neutrons, 16, and the number of electrons are 16. So when we take our positive protons and subtract our negative electrons, we end up with a neutral charge on the atom. Now it says we're going to gain 2 electrons. So for its ion, it gets 2 more electrons. So 2 more electrons are added, now giving us a total of 8 electrons. So now it's still a sulfur atom, so there are still 16 protons. Nothing's happened to the neutrons, so there's still 16 of those, but we have gained 2 electrons. So now the number of our electrons is 18. So now when we take our positive protons and subtract our negative electrons, we have 16 minus 18, and we end up with a 2 negative charge. So this is showing us that when it gains electrons, since electrons are negatively charged, it will become a charged particle with a negative charge on it. So atoms like sodium that lose electrons make positively charged ions, and atoms like the sulfur ion we looked at are going to make negatively charged. Now what happens when we change the neutron? Whenever you change the neutrons, we refer to these as isotopes. Isotopes of the same element. Those are atoms of the same element that have different numbers of neutrons. When you change the number of neutrons, since it is a neutral particle, nothing happens to the charge on the atom. It's still overall neutral. So it's different from changing the electron, where the electron changed the charge. The neutron does not affect the charge at all. What it does affect is the mass. As we looked at our particles, we saw that the proton and the neutron both have a mass of 1 atomic mass unit. So if I'm adding or subtracting the neutrons, that is going to affect the mass. So determine the mass of a hydrogen atom with 1 neutron. Well, we said to find the mass number, you're going to take the number of protons and add it to the number of neutrons. Well, Hydrogen is the first element on the periodic table. Its atomic number is 1, which means it has 1 proton. Then it tells us in the nucleus of this atom, there's 1 neutron. So that means its mass number is a total of 2 AMU, atomic mass units. So then here's a hydrogen atom, but this one has 2 neutrons. So it's still hydrogen, so there's 1 proton, but there are 2 neutrons. This gives us an atomic mass of 3 AMU. Then it says we have another hydrogen atom, but this one has 3 neutrons. So 1 proton plus 3 neutrons equals 4 AMU. These are all called isotopes of hydrogen. So 3 common occurring isotopes of hydrogen are hydrogen 2, that has 1 proton, 1 neutron, hydrogen 3, which has 1 proton, 2 neutrons, and hydrogen 4, which has 1 proton and 3 neutrons. A Bohr model of an atom is going to show what or how many particles there are in the atom itself. You've already seen me draw a couple. So a Bohr model, though, is going to show the number of protons in the nucleus, the number of neutrons in the nucleus, and then it's going to show the number of electrons on the outside in the energy levels. So we have to remember what we saw at the end of the History of the Atom Part 2 video about what Bohr thought about the energy levels. That was that the first one could hold 2, the second holds 8, the third holds 18, and the fourth holds 32. That's because the region of space, as you get further away from the nucleus, becomes larger, so therefore more electrons can fit in that space. But the nucleus is so small that then only right around it, only 2 electrons can fit there. So we make a Bohr model by showing the number of protons and neutrons in the nucleus and the number of electrons correctly placed in the energy levels. So we know this first energy level can only hold 2 electrons. The second energy level can hold 8 electrons. The third can hold 18 electrons. And the fourth can hold 32 electrons. Okay, so let's make a Bohr model of magnesium. Okay. This is called the nuclear symbol of magnesium with the numbers and the symbol. We'll talk about that in just a moment. You can use that and determine the element's pin, or the number of protons the number of electrons and the number of neutrons. We find that by just looking at our our symbol up here. This bottom number is how many protons there are. So there's 12. It's an atom, so it's neutral. So that means I have 12 electrons. And then with the neutron, the mass number is protons plus neutrons. So I can determine how many neutrons there are by subtracting 12 from 25. And I get 13. Then to make the Bohr model, I take my number of protons, and I can just simply, I don't have to put 12 positive signs. I can just write 12 P and a little positive. So I know that there are 12 protons in that nucleus. There are 13 neutrons in the nucleus. And then I have 12 electrons. Well, the first energy level can hold 2. Well, I definitely have more than 2. I have 12. So we know we're going to have to go to the next energy level. And the second energy level can hold 8. Well, 8 plus 2 is 10. I need 12, so that means there are definitely going to be 8 electrons here. And there's going to be electrons in the third energy level. Now, the third energy level can hold a total of 18. But right now, I have a total of 10, and I only have 12 electrons. So that means in the third energy level, there are only 2 electrons there. And this is what's called a Bohr model. You can, if you would like, instead of writing the numbers, you can make it by putting, like 2 dots or 2 slashes to represent the electrons. So I actually have 8 slashes on the second energy level, 2 on the first, and then 2 on the second, like this. So if you don't want to just write the numbers, you can do that if that helps you visualize where they're going. You can also do that. For the nucleus, though, I would definitely just write the number of protons and neutrons because that's such a small space, and some of them get fairly large, so trying to make that many positives and zeros for neutral in the nucleus would get a little confusing. So I would suggest just writing them like this. And then the electrons, you can either use dashes, you can use dots, or you can just write the number that are present. This is called the element key. This is the box that is on the periodic table for the element. It has the atomic number here. Usually the atomic number is given at the top of the box. I have seen periodic tables where the atomic number is down at the bottom, but the majority of them, like the one that's in our classroom and the one we will be using on quizzes and tests, have the atomic number in the upper portion of the key. Then you have N, the symbol, and then some of them will give you their name, nitrogen. Ours in the classroom does not have names on it, but it will always be up for your reference. And then the decimal number down at the bottom is the atomic mass. This is the weighted average of all the common isotopes found in nature. So all of the isotopes, like we saw hydrogen 1, hydrogen 2, hydrogen 3, those are all averaged together, but they're weighted, kind of like your grade for this class is weighted. So tests are worth more than homework. Then the mass is weighted because sometimes one particular isotope shows up more frequently than the others. So even though it's there, we want to show on the periodic table the atomic mass that's the average of what you would normally find. And so if we look at nitrogen, since this is so close to 14, That means even though there are isotopes of nitrogen, the majority of the nitrogen atoms that are found have a mass of 14. A nuclear symbol or the complete chemical symbol, it's the same thing. You'll hear them referred to as different, both of those names. It's the same thing. Just like we just looked at the one for magnesium, you're going to have the mass number up at the top, and that is the number of protons plus neutrons, and then the atomic number, which is the number of protons, down as a subscript. So if we look at this element, there are 10 protons. So I can look at the periodic table and I can see the atomic number 10 is neon. So that is my symbol. Then I can write a nuclear or complete chemical symbol for this by taking the atomic number, which is the number of protons, and writing that as a subscript, and then take the mass number, which is everything that's in the nucleus, and write that up at the top. That's how I'm able to determine the number of protons, the number of electrons, and the number of neutrons when I look at the complete chemical symbol or nuclear symbol, because I know atomic numbers on bottom, and the atomic number is the number of protons. So I can automatically fill that in. Then I know when we're dealing with atoms, they're all going to be neutral. So however many positive particles I have to have the same number of negative. So then I know my electrons. And then the mass number up here is the number of protons plus the number of neutrons. So then I can just subtract the two, because I know this is the number of protons. So if this is the number of protons, if I subtract that from 21, then I know how many neutrons I have. 11.